The USGS letters and slogan "Signs for a Changing World" appear in white in a flipping motion, then fade to black.
Hello, everyone, and welcome to the USGS Hydrography Community Call. I'm Karen Adkins with the National Geospatial Program User Engagement Office. This call is being recorded and will be made publicly available on the USGS website and on YouTube after the call once it has been approved for publication. Links to the recording will be sent out to subscribers of our Globe Delivery topic, the 3D Hydrography Program. So first, Steve Aichele, who is the National Geospatial Program Planning and Management Lead for Hydrography, will start off with a few announcements and updates.
All right, thanks, Karen. So a number of updates this cycle. First one is sort of administrative. There were a number of minor corrections made to the hydro acquisition specs. And again, these are the 2024 specifications that are actually not in effect yet. So this is an advisory state at this point. But there are a number of sort of minor corrections to some figures, some couple typos, that sort of thing. And those have been reposted to the specifications website as revision A3. Other items, some of you may have noticed we did get this implemented. The change from the general flowline feature type, these were originally called rivers, which was somewhat of a misnomer in that we aren't necessarily mapping rivers or streams for that matter. We're really identifying channels from the LiDAR imagery and IPSAR imagery. And so as a result, we've changed that code from river to channel line to reflect that it's more of a geomorphology kind of feature rather than an actual water presence feature, although we'll talk a little bit more about the water presence here in a couple minutes. We're making progress on HydroAdd3D. There are a couple more kind of IT gates we need to jump through. We are planning on opening a beta next month with that to run about 3 to 4 weeks. We'd like users to be using their own data for that if they can, so that we get some different experiences, some different use cases exposed. There'll be a SharePoint site set up, and assuming there aren't any giant glitches exposed, we're going to plan for a full release towards the end of the fiscal year, late summer. If you're interested in participating in that, email the 3dhp@usgs.gov address, and we'll add your name to the list. We're not looking for hundreds of people. We just don't have the we don't have the depth to support that. But we like to get kind of a mix of a couple dozen or so who have different geographies, different issues to try to work through. Again, just sort of test some various use cases. Finally, the email Dropbox, the nhd@usgs.gov is retired. We've broken that out into sort of 3 different categories. 3dhp@usgs.gov covers kind of general program information. 3dhp DCA@usgs.gov relates to the data collaboration announcement, acquisition questions. And then the TNM help address remains in effect, and sort of general National Map Product and Services questions can go there. Every once in a while, we get one rerouted from them. The next item is a little bit challenging, but many of you have probably watched the news, or if you're a Fed, you probably know it firsthand. There have been some significant changes in the federal staffing environment here in the last couple months. When we started the fiscal year, the Hydrography Program at about 39 FTE total, and had hoped to grow that by a couple over the course of the year. Rather than that, we've actually lost 5 recent hires, all from our data validation unit, which is kind of a big gap there. But we've also lost David Anderson, who many of you have interacted with over the years as our conflation expert and has recently been leading our ingest process development. Ryan Teeter, who was our specification specialist. And with Joel Scallett, Ryan and Joel taught the Intro to NHD class for many years. Joel Scala was kind of a jack of all trades in the program, and he's also retired. And then Sylvia Terziati, who we've all known as the person who assembled the EDH specifications, and was our science and applications lead within NGP, retired. So cumulatively, that's comfortably over 100 years of experience that walked out the door last week. So we have some gaps to fill. And as I mentioned, we had hoped to climb over 40 FTE this fiscal year, and we are now below 30. So we're still making progress on things, but some of these things are going to be slower. And we are looking at what items we might be able to either move off into the future or drop to try to maintain velocity on some critical items. That's sort of the state of things at the moment, and we will update that as we get more clarity on it. So all of that said, those are the announcements. The main topic we want to talk about today is actually the new probabilistic continuous value estimates flow. And these are the replacement for the old categorical, perennial, intermittent, and ephemeral classifications that have existed in the NHD and on the topographic maps before that. This is a fairly big shift in the way we're presenting information, but it's also a very big shift in the basis of the information. If you sort of think back, the old classifications were typically based on field surveys when those maps were originally compiled. So many of those go back into the 1960s and sometimes even earlier. And they were based on the conditions at the time and some conversations with locals. And so there's some significant variability in that. Conrad Hafen, who some of you may recall from a couple of years ago, actually wrote a dissertation chapter on how the perennial, intermittent, ephemeral classifications varied based on the drought index of the year in which the map was originally surveyed. So there are a number of challenges, never mind the questions of whether these things are out of date on their face. And so we wanted to move that categorization into a more more statistical probabilistic approach where we actually had a continuous gradient of values. And also, we're a little more transparent about what we knew and what we know and what we don't know. There are 30 million features in the NHD. We don't know a lot about a lot of them. And so what we're trying to do here is provide an estimate, but also provide an estimate of the uncertainty that goes along with that. And so some of these we have a lot of confidence in. Some of them we have less confidence in. And as we go forward, hopefully we can gather more data, gather more methods, and improve the confidence in particularly some of the headwater systems. One other constraint I do want to mention on this, we wanted an app. There are lots of applications out there, regional, state, sub-state sort of applications that do this sort of work, but they're based on very localized data sets, state geology maps, for example, or other sort of regional data sets. And we really needed something that applied CONUS-wide. And so that was one of the constraints going into this exercise, was to come up with something that was based on consistent input data CONUS-wide. And so that is a limitation. Local estimates may well be better. Probably will be better in many cases. But this is intended to provide a consistent consistent estimate across the country. So our speakers today are Stacey Archfield. She's a research hydrologist with our water mission area in USGS. She's been doing this sort of work, for decades at this point now, going back to some early work with some stream stats sort of things in Massachusetts a long time ago. And then Dave Blodgett, who I think we've heard from before on this call, doing a lot of work with main stems and high features and kind of the more conceptual aspects of some of the changes we're making here. Okay, now we'll pass it to Stacey.
Awesome. Thanks so much, Steve. So because this is going to be posted later and is recorded, I'll just make mention that this information is preliminary and it's subject to revision. And so that's just an important note that we're still maybe working to refine some of the things here. So we're just going to look at an update to the stream permanence work that Steve just motivated for us. So the goals of this analysis are to estimate through readily available information the probability of observing at least N0 flow days at a particular site in a river. And then ideally, we want confidence intervals on this estimates as well. So by our definition, readily available information is really limited. It's limited to the location of the river region space. So it could be like a HUC 02, 04, some type of spatial representation there, or level 2 ecoregion. And then also the size of the area drained to that particular location. So we want really basic information to use to make our predictions, things that are widely available across the United States. And this is the information currently or soon to be available in 3DHP. And I just want to emphasize, we consider this really a minimum viable product. So it's moving us towards that goal of probabilistic mapping of stream permanence rather than designations of perennial, intermittent, or ephemeral. But it really is like a first cut, given the limitations on the input data sets we have or the explanatory variables and the stream gauge network that we're using, which we know tends to be biased towards placing stream gauges where there's flow continuously throughout the year. And we're also assuming in this way then that spatial aggregation, a HUC or a level 2 ecoregion, is a surrogate for other possible explanatory variables that aren't available at the national scale. So physiographic properties, hydroclimatic properties, those types of things we hope could be represented by the spatial location of the river in a HUC or an ecoregion. Okay, and so then we're looking out at our stream gauge network, and we're looking at stream gauges in this Gauges 2 data set. This is a data set of about 9,000 stream gauges that have been operating for at least 20 years across the United States that have various levels of reference conditions, and those reference conditions are also classified. But we're going to be building off of this data set. And we're going to look at stream gauges that have at least 10 years of record, with each year having a complete set of daily observations. So every one of those years has to have 365 days of flow or 366 days of flow within them. That leaves us with about 7,700 stream gauges, and that's regardless of the reference conditions. So we're lumping all stream gauges together, whether they're there's no upstream alteration or minimal alteration in the basin, or there could be things like urbanization, dams, water use, other things like that. But again, for the minimum viable product, we needed to maximize our sample size. Each stream gauge has the following information. So we know the drainage area that's drained to that particular stream gauge. We have the HUC 2 level in which the stream gauge is located, and then the level 2 ecoregion in which the stream gauge is located. What we did was basically test out whether HUC 2s or level 2 ecoregions. And then I mentioned at the end of the talk, but I'll mention now, we're looking at even further higher resolution HUCs like HUC 04 to see if we could parse out the data set in that way. Sorry, my nose is a little running. Allergies is in full swing here in Virginia. Okay, so for the daily flow metrics, we modeled initially 3 different probabilities. So the probability of observing at least 1 zero flow day on an average annual basis, the probability of observing at least 7 zero flow days on an average annual basis, and then the probability of observing at least 30 days of zero flows on an average annual basis. And so just to understand more about how we computed that, what we did was, so for example, say we have 10 years of complete record at a particular stream gauge. For each of those 10 years, we count up the number of 0 days of flow that were present. So each of those 10 years might have different numbers of days of 0 flows present. And then we average over those 10 years, the average number of 0 flow days present to get this average annual number of 0 flow days over the record. And that's the variable that we're using to model. And so as you might imagine, because as I alluded to earlier, our stream gauge network tends to be placed on rivers where we have continuously flowing river or continuously flowing water. As we increase our n number of zero flow days present, we get less and less stream gauges that have that number of zero flow days on an average annual basis. So what I'm showing here is by HUC, with the map of the HUCs on the left, we're seeing what fraction of stream gauges have at least one zero flow day here on the panel on the left, what fraction of the stream gauges within that HUC have at least 7 zero flow days, and then on the right, which fraction of stream gauges within that HUC have at least 30 zero flow days observed on an average annual basis. And again, what you could see, particularly in the eastern United States where these HUCs are located, east of the Mississippi, we see fewer stream gauges, fraction of stream gauges in those HUCs that have at least 7 zero flow days or at least 30 zero flow days on an average annual basis, and even at least 1 zero flow day. There's some smaller sample sizes here that we're going to use to develop our models. This is just showing that same plot, but with the fraction of gauges that see at least 1 zero flow day, 7 zero flow days, or 30 zero flow days. And that's just by level 2 ecoregion. Just wanting to see if maybe if we broke things out in this particular way, we might end up with a different set of sample sizes to develop our models. Okay, and so the approach we're going to be using is called survival regression. So survival regression is common in health sciences, but less so in hydrologic data. It's mainly used in hydrology to deal with sensor data. And I'm actually the course coordinator for the USGS Environmental Statistics course and the author of the recently updated textbook. And we talk about sensor data from that perspective, and the use of survival regression is really through the use of sensor data. And what survival regression estimates is the probability of an individual surviving past a certain time t. What we're going to do is change that sentence into looking at the probability of at least n zero flow days being observed beyond a drainage size A. So that's how we're going to look at survival. We're going to think about how do zero flow values die off as our drainage area size increases. And survival regression also allows us to include, but then censor the large number of gauges where no zero flows are observed. The other thing that survival regression will do is enforce the probability that at least n zero flow days being observed decreases with increasing drainage area size. So within at least the unit that we're making our model, like a HUC2, for example, we know that the model will always show flow accumulating or zero flows dying out as drainage area accumulates downstream. Now, we understand that that's a limitation because of the potential for areas of the country where there are losing streams, but that's one of the assumptions that we're making here. We see it as, at least for this minimum viable product, an advantage of this method. And then in survival regression, we can estimate the probability of observing at least n zero flow days for a given drainage area size, and then the 95% confidence intervals on that probability. And so here's what the survival regressions are going to look like. And I'm just going to scroll through and show you for different HUCs what the survival regression curves look like. And then Dave is going to show some results mapped to 3D-HP. So we're going to look at a graph that's going to show us drainage area and then the probability in this case of observing at least 1 day of zero flow on an average annual basis. And we're looking at how those zero flow days die out as a function of drainage area. So as the probability approaches zero, as drainage area gets larger and larger. So the probability of observing at least 1 zero flow day gets smaller and smaller until it eventually gets to zero. As with any regression approach, the estimates are limited to the training data set. So that is, we are limited to the range of drainage areas under which the models will develop. So in this case, we're limited to about 1 square mile to, something much bigger than maybe 50,000 square kilometers. Sorry, in this particular HUC1 with 299 gauges. So we're discussing the possibility of coding anything below the smallest observed drainage area is unknown, or we're trying to figure out how we might want to represent things that are out of sample, estimates that are out of sample. And for survival regression, confidence intervals have been shown to perform well with samples as small as 25 and up to 50% censoring of the data. So what we see here is with a probability of 1, these are all the stream gauges out of the 299 gauges in this HUC1 unit. this is telling us these are cases where we saw at least one zero flow day present on an average annual basis. Each one of these dots could represent more than one zero flow day on an average annual basis, but it's at least one day has been observed up here. And then in the bottom, we see the stream gauges for which we had no cases where there was at least one zero flow day observed on the bottom. And so what the survival regression does, let me see if I have this in the other thing, I'm sorry, I'll mention that the other thing survival regression results can show you is the probability of 50%, this drainage area for which half the time you have a probability of basically seeing a zero flow day, at least one zero flow day, and then a drainage area for where there's like half and half basically, or there's a 50% chance you don't see at least one zero flow day. And sometimes that's interesting too. Okay, so the last thing I'll just mention, since that's the last slide on this, is that you'll see here, this is part of the censoring aspect of this, is that the steps only occur, survival regression is purely empirical approach that relies solely on the data, the underlying data. So there's no model that's being fit to this. It's just a series of probabilities, simple probabilities that you calculate based on the number of essentially stream gauges that have died that we don't see any more zero flows versus the total number of stream gauges. And so because we're censoring all the stream gauges that do not have any zero flows, we only see steps in the data when we actually have an event, that event being that we see at least one day of zero flows here. And so you can see the steps don't really change. So when we have a lot of observations at the top here, where we see a case where we see a lot of stream gauges within a particular HUC that have n number of zero flow days observed, we're going to get a much smoother, the staircase you'll see will be much more smoother, as well as the prediction or the confidence intervals as well, not prediction intervals, confidence intervals. So I just wanted to make note of that too as we go through the HUCs. So I know this presentation, I always debate whether to spend the time making this look savvy or just focusing on the results, but I think making it look a little less savvy, you know, really emphasizes the minimum viable product aspect of this rather than, trying to make things seem a little bit more fancier than they are. But here's the graph that we just saw on the left. This is the survival regression curve for the stream gauges that are available in HUC 1, which is the Northeast United States. And you could see here that we have a lot of that. Basically, it dies out pretty quickly. The presence of zero, at least one day of zero stream flow, dies out fairly quickly as we move along and get to smaller and smaller probabilities. Again, that's the smaller and smaller probabilities mean the less and less chance of seeing at least one zero flow day. And of course, we could do this for at least 7, at least 3 zero flow days, whatever number of zero flow days might be of interest. We can develop these empirical survival regression curves for that. Here we see HUC 2. We actually have a little bit more HUC 2 starting to get in the mid-Atlantic US. We can see we have a little bit more data to work with, and then therefore our confidence intervals are looking a little tighter where we have more data, and we have a smoother curve when we have more data. HUC 3, at least we have a lot more uncertainty at the beginning where we have very few stream gauges that look like they might have a case for at least one zero flow day until we get out much more dense data set, and then we have a smoother curve and smaller prediction or confidence intervals. I'm so sorry, they're confidence intervals, not prediction intervals. And then we can just look through one of the things that I thought Sylvia, I want to give Sylvia credit for this, is that the HUC 3 region has a lot of varied hydroclimate properties. You have coastal, you have inland, you have mountains, and then relatively flat areas. And so we broke out that particular HUC into 3 different sections, the west, south, and north. And you can see here in the west, we don't have a lot of observations. So we get this really weird looking survival regression curve, but we do have a much smoother one for HUC 3, O3S, and then we have on the right O3N north. And you can see the survival curves are somewhat different, particularly for this O3 West. Things die out pretty quickly there. The zero flows die out pretty quickly. HUC 4, we don't have a lot of stream gauges that have zero flow days, so we have very few to create this model. So these are things that we need to think about, or we're thinking about how to represent on a map when you have such few observations. And then HUC 5, you can see that the survival regression curve is very smooth because we have a lot more observations. We actually combine HUC5 and HUC6 because HUC6 is so small and put them together into this one model. And then here's some other ones just to show you. So you can look at HUC7, looks a lot like some of the Eastern survival regression curves, but you could see here, let's contrast that with HUC9, where we see there's zero flow values observed even when the drainage area is large, and to some extent it takes a while for the survival regression curve, longer than some of the other curves, to die out, because we're just seeing even at higher and higher drainage areas in square kilometers, we're observing at least 1 zero flow day. So the curve is shifted to the right and not dying out as quickly. And then we have HUC10 upper and lower. We did separate those two HUCs out to see what happened here. And you can see we have so few values, so the confidence intervals are very, very wide on the probability when you have much smaller drainage areas in the HUC10 upper or 10U. So we're almost done going through the country, and then Dave can show you how some of these are represented. But here, HUC11 and HUC12, we actually have, as you would expect in this part of the country, we have much more gauges that have at least 1 zero flow day present. And so we're able to have really smooth survival regression curves with really tight confidence intervals because of that. Because we just have more empirical data to fit to the model. And then here's 13, 14, and 15 in the Southwest United States. They actually are kind of interesting. You can see the contrast between how things die out quickly in HUC14, which is kind of in the Utah, Colorado, Western, is that Western? No, sorry, failing on my states here. Wyoming, Colorado, sorry, and Utah. You can see that things die out actually pretty quickly here in terms of the survival of at least observing 1 zero flow day versus HUC15 and HUC13, where it takes a little bit longer for to reach a drainage area where you're sure you're getting a probability of never observing at least 1 zero flow day. And then we're just going to walk through the Western United States, and hopefully you're getting kind of a feel now for these models and how the observations affect the confidence intervals and the predictions. But this would be what we would be using to map out stream permanence. Okay, so just some takeaways. Survival regression is a potentially useful, and it's a parsimonious method, meaning like it's really, requires one explanatory variable and essentially your estimates of the number of zero flow days that have been observed on an average annual basis to assign probabilities of observing these zero flow days. Confidence intervals are also possible. These are empirically based as well. We're thinking about how to represent uncertainty on a map. For zero flow days occurring at the 7 and 30 day periods, we have that information. I'm not just showing it here for time constraints. But there are some HUCs in level 2 ecoregions that only have enough data to support modeling. We still need to report out goodness of fit metrics for each model. We're also considering refining the HUC regions in some areas, going down to the HUC4 level from the HUC2 level. So seeing if we can lump maybe HUC4s in a different way. Dave will show you some examples, maybe perhaps where when you have a break in 2 HUCs, there's some discontinuity in the estimates. And so that's one of the reasons we're thinking of refining there. And then lastly, I think, and most importantly, this is really a minimum viable product. I think the overall goal is that it gets us to that philosophy that Steve mentioned, moving away from hard classifications and more towards a probabilistic approach, and it really provides immediate results for inclusion in 3DHP products. But the hope is that national data sets and models would be incorporated into future estimates or replace these models. Every time I give this talk, I say I have no emotional value associated with these models. I think it's important that we have a product that is reasonable, that makes sense statistically, but really the hope is that we continue to advance like science should. We can see how some of this looks then by having Dave plot it up.
I just have a little QGIS project that I can share a little bit of what this looks like using kind of one kind of no frills symbology. So what you're looking at right now is just a collection of 4-digit HUCs that I've run this for. I have it nationally, but it's much harder to visualize. So we'll use these as examples. And the first, so the first thing I guess I want to show is when you zoom out and look across the country, how this is symbolized right now is the darker blues are low probability of one or more zero flow days, and as you get toward yellow, you get toward higher probabilities of one or more zero flow day. And kind of as you would expect, things are drier in where you would expect them to be and wetter in places you would expect them to be. And if we zoom in, I especially like this region here. I think I want to use, I don't know if this was the confluence I was going to use, but this will work. So what we're looking at here, possibly if I turn the base map off, it'll be easier to see. What we're looking at here is the upper confidence interval. So this is this is a reflection of our highest estimate of the probability that there is one or more zero flow day. And I have to slowly think through how I'm going to say that. And it starts to make more sense if we switch to the other ones. So if we, so here's our lower probability, and you can see lower probability, we're seeing darker colors, which is saying it's less likely that there's one or more zero flow day. The prediction, which this is slightly lighter colors, basically saying our best estimate of one or more zero flow days is the values you see now. And if we go to the upper probability, it gets should get even lighter. And I had a better example area, maybe to illustrate this. You really can't see the difference. I thought my example, you can really see it between the lower and the upper, or the lower and the central. But if we just switch between the lower and the upper probability, you can see that there is a range of probability estimates for what the likelihood of one or more zero flow days is. And the last layer I have to show here is we can also visualize the range of probability. And here, the lighter colors, the red to yellows, are where we have a narrower range of probability. And this is the location I wanted to show because it's got a nice gradation. So you can see in this region, we'll look at our probabilities here. It's very likely that we have no zero flow days on a reach up here, and the probability range is quite narrow. So we have a high degree we have a lot of confidence that there's probably continuous flow here. But in contrast, as you get into these smaller reaches, the probability range is higher, and the likelihood, if we look at the upper versus lower, the actual prediction of the likelihood of zero flow days is somewhere, in the 50%, with a somewhat wide kind of range of probabilities that could be, right? And so I show this to try to illustrate the data. I'll just select one feature and show you the numbers we're dealing with here are probability, the upper and lower probabilities, and a central prediction, and just an interval. So there's actually four. Obviously, what I've been showing is there's kind of four values that we can visualize, and the plan is that these four values, or at least the three, and you can calculate the fourth, would be made available essentially by 3DHP identifier. Exactly how that gets baked into the data set is largely to be determined. But one way or the other, an estimate of the likelihood of some number of zero flow days is in our future. So I think that's pretty much what I wanted to show. I don't know if Steve, you want me to try to illustrate any other nuances of this, but I could go to some other region and kind of show a little bit of a contrast.
I think it'd be good to look at maybe go out to just sort of the HUC4 level there and show some of those, show the different layers exposed across a couple different HUC4s to get some of the contrast between, the southeast, for example, where we have lots of water, right?
So, and I tried to set this up so the symbols draw in a way that you can actually see things, but like this 1810 HUC, the probability range is very narrow because we have a lot of stream gauges that have zero flows. So there's actually a lot of confidence out here in the prediction. But up here in region 10, especially in small rivers, we don't have as much data. So the confidence bands are much wider for the smaller rivers. So I guess that's one thing to show. And it's the more I've looked at this stuff, kind of the more questions I've come up with, and for the most part, they've added up. If we look at these probability bands, obviously the probability band is narrower for larger rivers, so you're actually seeing some of these. We can go into the Delaware once. And this is full resolution NHD data, so it takes a second to render. But if we look at our if that's going to draw. So as you would expect, larger rivers, you're seeing this kind of stream order-ish pattern where larger rivers have a lower probability of zero flows. That lower probability band versus upper probability band, you're just going to see more. I think I can switch back and forth now that it's drawn. Yeah, you're going to see just a slightly increased probability of the prediction being that there's one or more zero flow days with the upper confidence bound. So that's kind of, yeah.
How about zooming in on the main on a major channel there, and just sort of demonstrating the difference in the values between a main channel that has a very low probability and a very low uncertainty, and maybe a more peripheral channel that may have a higher probability and a higher uncertainty.
Sure. So obviously the Delaware River is actually fully zero, right? That may be extreme. Say we go to something or in between. Yeah, so these are all, once you're over a certain drainage area, they're coming back as zero in this area as we go upstream. Here's a 350 square kilometers, and the probabilities are very close to zero, but they're non-zero. And as we work our way up, here we're up to 23 square kilometers, and the interval is 25% because the lower and upper probability, the upper and lower estimates are 10% to 34% at this drainage area. There could be a zero flow day in this region, right? And what we're seeing in some of these models is this is a really smooth drop off, and in other models there's kind of a sharp cutoff where once you cross that drainage area for that region in general, you would expect zero flow days to occur. And in this one you can really see this gradation, where once we're up here at, what do we have? Actually, that's multiple features. Here we have 7 square kilometers, and the probabilities between 22 and 72%. Right. So I think that probably illustrates what you're talking about.
Yeah, that's a reflection of, we just don't have a lot of data to drive, estimates at that level of detail. Actually probably anywhere, but certainly in this region.
Yeah, and these places where the confidence intervals are fairly narrow, things tend to make more sense than where the confidence intervals are really wide, because there's a lot more kind of, the predictions have a lot of threshold behaviors in the areas where we just don't have very much information. But those thresholds are kind of artifacts. They're not what you would expect in the real world. We just don't have enough data to get those gradations into the predictions. But yeah, visualizing the probability range has been interesting, because the way I've got this visualized, this is emphasizing where uncertainty is. So the more red or blue is higher uncertainty, and where you don't see it as much is lower uncertainty. So it's kind of where the big rivers disappear, because that's where we have decent information, and the small rivers are highlighted as the places where uncertainty is especially high. And it's kind of trying to visualize those confidence bands, or that range of uncertainty.
Just a couple comments, and if we have any questions, we can field those as well. Again, we've said this a couple times, as a minimum viable product kind of instance, to move us off of those historic perennial, intermittent, ephemeral classifications. This in no way excludes, and in fact we encourage, local models to be addressed to 3D HP data as well. If the main challenge is finding consistent predictor data sets across the country. I saw a chat go by here about the Massachusetts StreamStats model, for example, and getting consistent CONUS-wide data to work with is pretty challenging. I'd also mention we're doing this on a fairly tight time frame and a fairly small budget. So we're trying to come up with something of a placeholder of a move in the right direction, a minimum viable product, and look for refinement in the future. Appreciate everybody participating. If you have questions, feel free to email any of us, and and we will have another one of these in 3 months, and I forget the date off the top of my head, which will make Karen very disappointed in me. But we will talk again, and we'll continue to use this mechanism to share information. So thank you all for dialing in. Have a good day.
The USGS letters and slogan signs for a changing world appear in white in a flipping motion, then fade to black.